Now, on to the presentation. What? Removing capacitors lowers the inductance? How can that be? My basic circuit theory class says that inductance in parallel reduces the inductance, which means that more capacitors should be better. This is why we are engineers. The correct answer is, it depends. Here we are showing a typical FPGA design where simulation has made it easy to create an EM model of the PCB power delivery network and then evaluate what happens when capacitors are optimized to provide the optimum impedance for a given load. For this given set of capacitors, it was found that turning off the smallest caps that were off to the side of the FPGA, the group B capacitors, actually reduced the inductance in the path to the FPGA pins, only 32 picohenries in the impedance versus frequency graph on the left. Turning these group B small caps on made the impedance worse, 44 picohenries in the impedance graph on the right. The very small caps directly under the FPGA package have the lowest inductance to the FPGA pins, but adding more of these same value small caps off to the side of the package does not make the PDN better for the load. This result is what inspired me to team up with Steve Sandler of Picotest and Jack Carroll of Xilinx to write the DesignCon 2021 paper, Capacitor Placement Strategies for Optimum Power Integrity, and is the basis for today's webcast. The agenda starts with some basics on power delivery and why flat impedance design is the goal. Then, the capacitor selection and placement will be looked at from different perspectives. For example, what does the VRM need? What does the load need? And what types of models are needed? The special case of capacitor-to-capacitor resonances will show the danger of not designing for flat impedance. Finally, an FPGA case study will be used to run simulation experiments on capacitor placement strategies. Power integrity is all about designing for a target impedance across a wide band of frequencies to deliver power to the load. Looking at the power delivery versus frequency shown in this graph, something interesting can be seen. The VRM is not the only source of power. In fact, the VRM looks like a low-pass filter shown in gold because it only delivers power at low frequencies. At high frequencies, the VRM control loop cannot keep up, and its output impedance acts like an inductor and increases with frequency. This is often called the active inductance of the VRM output, or voltage regulator module. A series RL model can be used to model this low-pass behavior. At the frequency where the VRM stops delivering adequate power, it is then the job of the decoupling capacitors to take over. However, capacitors are not ideal, and at frequencies beyond their self-resonances, they become inductors, and they also stop delivering power to the load. The decoupling capacitors look like a bandpass filter, shown in blue, that can be modeled as a simple series of C, R, and L. Finally, at the gigahertz switching frequencies of modern-day digital electronics, it is the job of the package capacitance and on-die capacitance to deliver power. At low frequencies, the package die capacitances do not have enough charge storage to deliver power, but at high frequencies, the impedance drops and acts like a high-pass filter shown in pink. This high-pass behavior can be modeled as a simple series RC. This graph clearly shows that the source of power depends upon the frequency. Combining these three power sources, low-pass, bandpass, and high-pass together in a schematic shown at the top of the slide, and then exciting them with a swept frequency AC load can result in the big V impedance versus frequency as shown in the bottom left graph of impedance. The impedance peaks are the result of an inductor resonating with a parallel capacitor, like the VRM active inductance with the decoupling capacitors C, or the decoupling capacitors ESL with the package capacitance. These resonances can be minimized by optimizing the decoupling to match impedance. To match the VRM, set the total decoupling capacitance equal to the VRM active inductance divided by the target R squared. At the higher frequencies, to match the package capacitance, simply reduce the PDN inductance until it is equal to the package capacitance times the target resistance squared, as shown in the equations here in the top schematic. This optimized selection of the PDN capacitors results in the resonant-free flat impedance design shown in the graph on the bottom right. The very simple estimate for flat matched impedance is based on transmission line theory, where the characteristic impedance Z0 equals the square root of the inductance over the capacitance. This characteristic impedance is where the inductive and capacitive impedances are equal for a given impedance. And the behavior looks like a resistor with voltage and currents in phase, and there is no resonance. The flat Z design matches the impedance between power delivery domains. To really show the benefit of the flat impedance design, simulation can be used to excite these impedance profiles with a dynamic load in the time domain. Here is a PI ecosystem voltage ripple time domain simulation that compares the performance of the big V non-flat impedance design in the top left graph versus the flat impedance design in the bottom left. In simulation, it is easy to change the AC sweep that generated these impedance plots to a dynamic transient pulsed load to simulate voltage ripple versus time as shown in the graph on the right, when the impedance profiles are excited by a 2 amp dynamic current. The graph shows the dynamic current at the bottom in black, pulsing on and off versus time at 178 kilohertz to excite the first impedance peak in the big V design. Then, at the peak of the first frequency, the second resonance is excited with an additional dynamic load at 12 megahertz. The resulting excessive voltage ripple shown in red is often called a rogue wave, since the voltage ripple of the two resonances can add together if the two voltage peaks happen at the same time. Multiple impedance peaks in the frequency domain can create rogue voltage waves. Now, look what happens if the impedance is flat with no resonant peaks. Exciting the flat impedance design with the same dynamic current as before results in the voltage ripple shown in green. Here, we see that there is no exponential ringing, but rather a critically damped system with a simple delta IR voltage drop due to the changing current and path impedance. EDA tools like Keysight's PathWave ADS make it easy to run these simulations and explore the relationship between controlling the impedance in the frequency domain and the impact on worst-case noise in the time domain. The first section showed us that flat impedance is the design goal, but how easy is this to do? The next section will look in more detail at what it means to select capacitors for the PCB PDN, the voltage regulator module, and the load to get the most out of the power delivery network. Paralleling capacitors to get more capacitance and lower inductance is a bit tricky. The physical location and the measurement points can result in some odd behavior. This simple PCB in the top left has 5 side-by-side capacitors mounted in parallel. You might expect that paralleling 5 identical capacitors will result in 5 times the capacitance with 1/5 the resistance and inductance. But due to small parasitic inductance in the circuit board, the parallel capacitors will not necessarily act the way you expect. The EM simulation shows that while the capacitance is 5 times greater, the resistance and inductance are only half of what is expected, and the results are not the same as a simple lumped SPICE simulation, shown in the schematic on the bottom left. The lumped SPICE simulation gets the wrong inductance and makes it difficult to predict PDN resonances. the SPICE simulation can get it right if we knew what parasitics to add between components, but it is much easier to use an EM simulation tool. The PathWave ADS PI Pro EM simulation tool uses an FEM simulator to generate an S-parameter EM model of the PCB PDN with ports for all of the decoupling capacitors. This EM model that includes the PCB parasitics and capacitor models is the best way to optimize the capacitor selection and placement. This same example PCB with 5 parallel capacitors can also be used to show what happens when each capacitor has a different value. The 5 parallel capacitors are selected from large to small with decade spacing in values. Due to the small parasitic PCB inductance, the impedance looks different depending on the location of the impedance measurement. The impedance seen by the VRM next to the large capacitors, shown in red, is very different at high frequency from the impedance seen by the load, shown in blue. The lumped SPICE model, shown in black, gives a very different result, and even worse, it does not show any difference between measuring at the VRM versus the load because it lacks the PCB parasitics. The simple lumped SPICE simulation fails to predict the difference in power rail noise at the VRM versus the load. The EM model of the PCB gets the PCB parasitics correct and clearly illustrates how far off the impedance results can be for low impedance power delivery networks at megahertz frequencies. This illustrates why optimizing the PDN impedance may require optimization at more than one location on the power delivery network to avoid resonant noise sources. Capacitor selection is always about fighting the inductance in the capacitor's power delivery path that will result in an LDIDT voltage drop. Using multiple parallel capacitors will reduce the inductance, but the most efficient way to minimize the inductance of the capacitors is to improve the connections to the buried power and ground planes. To show the impact of via placement and PCB stackup for reducing the path inductance for a capacitor mount, Steve Sandler fabricated these small test boards and measured them. The inductance of the ceramic capacitor itself is mostly a function of its size, and these small capacitors are approximately 300 picohenries. The rest is due to the circuit board connections or mount. This example shows 2 identical capacitors mounted to a 2-layer FR4 printed circuit board. The blue board is 63 mils dielectric, while the green board is only 8 mils dielectric. The same Gerber files were used to produce both boards. Each board has 2 identical capacitors mounted. One uses 1 ground via and the other uses a small island with 12 ground vias to ground. The additional vias reduce the inductance, and so does the thinner circuit board dielectric. The added vias are most effective when the ground plane is further from the power plane, and the bigger impact is the reduction in the dielectric thickness between the power and ground layers. Here again we see the importance of using an EM simulator to calculate the mounting parasitics. Results show that the power and ground layer spacing is just as important as via location when designing the mounting footprint for a capacitor. Remember, I mentioned at the beginning, capacitors are not perfect, and they eventually turn into inductors at higher frequencies. This means that the biggest challenge in selecting the right capacitor is identifying the inductance that is impeding power delivery and to adequately compensate for that inductance to maintain a flat impedance. Here in this graph of impedance versus frequency for a power delivery network, we can start at low frequency at the VRM, shown as the black trace. The active VRM inductance divided by the target impedance squared can be used to get an estimate for the first bulk decoupling capacitance. This could be a group of parallel caps to get the desired ESR and minimum ESL, but regardless, this first bulk decoupling capacitance will have a limited bandwidth determined by its ESL. A second decoupling capacitance is needed with lower inductance to get to a higher frequency. Since the inductance that requires compensation is now lower for this second capacitor, less capacitance is needed and a smaller package size can be used. A smaller package size has less inductance by reducing the loop inductance between the power and ground connections. In this example, the inductance from the first bulk capacitor is 875 picohenries, and dividing this by the target impedance squared of 24 ohms squared results in a 1.5 microfarad capacitance for the next capacitance to maintain flat impedance. This 1.5 microfarad capacitor has less inductance, only 100 picohenries, and extends the flat impedance to a higher frequency. Clearly, inductance is what determines how much capacitance is needed, and inductance is what limits the bandwidth of a capacitor. If the inductance is such a critical parameter for capacitor selection, then one would think that the vendors would get it right. Sadly, the vendor models have not kept up with the fidelity needed for designing milliohm power integrity delivery networks to meet the continuously decreasing voltages and increasing currents of high-density, high-speed digital electronics. This slide is borrowed from an EDICon 2021 webcast on partial inductance that was presented by co-author Ben Dannon of Northrop Grumman Corporation. The measured capacitor data is for the 3 capacitors shown in the upper left. They are all 0805 package sizes, but the vendor data indicated that the AVX X7R had 709 picohenries of ESL, while the Murata capacitors were much lower at 400 and 340 picohenries. Careful measurement with calibration and methods to de-embed the mounting inductance resulted in the impedance plot shown in the middle. The measured data with mounting inductance removed shows that there is less than 40 picohenries of difference between these 3 0805 capacitors, and that what we thought was the worst capacitor with 709 picohenries is actually the best capacitor with only 140 picohenries of internal ESL. I hope that this slide convinces you that all capacitor vendor models must be verified with measurement. Just remember that capacitor placement optimization with incorrect models can lead to wasted engineering efforts. There are different methods to measure capacitors and different types of calibrations to remove the fixturing and mounting inductance, but not everyone agrees. Steve Sandler is an expert in the industry with years of experience modeling capacitor, and he has found the simplest and most reliable method to be the one where the mounting inductance is determined by shorting the power and ground pads of the capacitor footprint together, as shown in the picture on the upper right. The measurement is done with a VNA using a 2-port shunt configuration to get measurement accuracy in the microohms. This measured mounting inductance can then be de-embedded from the measurement of the capacitor mounted to the same PCB footprint, but with no short. This results in a capacitor model with the mounting inductance removed and is exactly what is needed for connecting to an EM model that already includes the mounting parasitics. The graph on the left shows the comparison of the vendor data in black of a 47 microfarad capacitor to our measurement in red, and then the even larger difference when the mounting inductance is removed, shown in blue. The PCB-EM model already includes the mounting inductance, so make sure to use a capacitor model like the one shown in blue here with all of the mounting inductance removed, or it will be counted twice in your simulation. I mentioned that the active inductance of the VRM will determine how much bulk capacitance is needed to design a matched resonant-free transition from the VRM power delivery to the PCB PDN decoupling capacitors that deliver power at the frequencies that exceed the bandwidth of the VRM. That sounds simple, but sadly the active inductance of the VRM is not a parameter that shows up on the data sheet. The equations that solve for the active inductance of the VRM will depend on the type of a regulator being used. In the top left, the low dropout linear regulator active or excess inductance is described by Shockley's equation. The switching regulator shown on the bottom left is a bit more complicated. Steve Sandler, in his book Switched Mode Power Supply Simulation, shows how the steady state state space average switching regulator equations can be solved for this active or excess inductance of the VRM. To first order, the inductance is related to the bandwidth of the VRM control loop, since it is this inductance that shows the decreasing ability of the regulator to keep up with the regulation as the frequency of the load increases. The best way to determine this active inductance is simply to measure it at the output of the VRM across the first bulk capacitor. If this inductive slope is not visible in the measurement, then it is often necessary to reduce some of the bulk capacitance to see this inductance start to dominate in the measurement. Looking at the graph on the right, we can see that increasing the bandwidth of the VRM reduces the active output inductance, and according to our equation for flat impedance design, where C equals the inductance divided by the target impedance squared, the total C required is less if the VRM inductance is reduced. This is one of the reasons why wide bandgap semiconductors like gallium nitride are so exciting for power delivery. The higher bandwidth, higher switching frequency of a GaN regulator greatly reduces the size of the bulk decoupling capacitors, which reduces cost, size, weight, and potentially, with fewer parts, can increase reliability. The VRM active inductance determines the low-frequency start for the decoupling capacitor power delivery. But how high in frequency must the PCB PDN operate to deliver power to the load? Jack Carroll of Xilinx supports worldwide customers on signal integrity and power integrity issues when designing FPGA applications. He came up with this very informative analysis. An S-parameter model of the package die power delivery network enables valuable information to be shared on the frequency-dependent behavior of the FPGA without the need to share proprietary internal design information. This simple black box S-parameter behavioral model of the package die makes it possible to connect 3 test case PDN designs to it. One is an open with no power delivered from the power delivery network to the FPGA. One is a matched 5 milliohm impedance PDN, which is an ideal PCB PDN with no limit on the bandwidth. And finally, the third case is a short with no resistance and no bandwidth limit for the power delivery to this FPGA load from the PCB PDN. The impedance graph on the right shows the result. The downward slope of the open test case in red indicates high impedance with no power delivery at low frequencies, but the downward slope shows that this is the internal package capacitance that can deliver power at higher megahertz frequencies. There is also an impedance peak in the tens of megahertz showing the Bandini mountain caused by the inductance of getting from the package into the die and resonating with the on-die capacitance. It is very interesting to note that the real resistance of the PCB PDN can help to reduce this peak as shown by the matched 5 milliohm PCB PDN example versus the ideal short in blue. In all 3 cases, we can see that starting in the tens of megahertz and definitely above 100 megahertz, the printed circuit board PDN has no impact on the power delivery to the die. It doesn't matter whether I have an open or a short. There is no change in the impedance above 100 megahertz. Remembering the 3 power delivery domains, we can clearly see with this analysis of the package die model that there is a limit to what the PCB PDN can do at higher frequencies. The real requirement for power delivery to the load is in terms of controlling the amount of noise ripple that makes it to the die. Here again, one can use the package die model and input an AC noise ripple at the FPGA pins and see what the noise transfer to the die looks like. At low frequency, any power rail ripple will be transferred 1-for-1 to the die power rail, indicated here by 0 dB gain. However, like we saw in the impedance analysis plot in the previous slide, the noise transfer is heavily attenuated at the higher frequencies above 100 megahertz. Not all packages are created equal, so selecting a high-speed digital device with a good package die PDN design can greatly reduce the bandwidth needed for the PCB PDN decoupling. Now that we have covered the min and max frequency range of the PCB PDN decoupling based on the VRM and the load, we can start to look at placement. One of the biggest problems with not understanding how flat impedance design can vary by location due to PCB parasitics is the problem with capacitor-to-capacitor pi resonators. Classic circuit analysis shows that an inductance in parallel with a capacitance can resonate. The inductance from a large capacitor, as shown in the schematic on the left, can resonate with the capacitance of a parallel smaller capacitor. This resonance shows up as an impedance peak in the impedance versus frequency plot on the right. Any path inductance, such as a via connection between the two capacitors, can make this resonance worse by increasing the inductance without a significant increase in the real resistance. The equation for Q, or sharpness of the resonance, shows that the peak height can be reduced by increasing the total real resistance. Very low PDN resistance can make these resonant impedance peaks worse. Here is an example of bringing power onto a printed circuit board through a power connector where a large cap has been placed on one side of the board and then a small cap on the opposite side, as shown in this 3D model in the upper left. Simulation of the impedance versus frequency at the large capacitor, shown by the red trace in the graph, may look okay, but due to the pi resonator that is formed, there is a huge impedance peak seen at the small capacitor location, shown by the impedance peak at 30 MHz in the blue trace. This large impedance peak also indicates the potential for significant radiated EMI at the small capacitor if this resonance is excited. Remember that the PCB parasitics are what make these two measurement locations so different. The PCB EM model, in this case, shows how the inductive vias and plane cavities are making this resonance much worse at the small cap location. Why is a pi resonator so bad? Because it creates high dynamic currents between two components, creating a significant noise source when excited. The top left impedance plot shows a pi resonator formed by a 22 microfarad capacitor connected with vias to the internal power plane and then to a second, smaller 470 nanofarad capacitor. EM simulation of the current densities clearly shows high currents between these capacitors and that these currents are not flowing to the FPGA load. Steve Sandler has also done measurements to show the existence of this problem using an LTC 3880 VRM demo board shown in the bottom left. Here, the large capacitor C13 is resonating with the smaller C18 and C19 capacitors at 30 MHz. This shows up as a near-field radiated noise at 30 MHz near the small capacitors, shown in the middle green measured frequency data. Another pi resonator forms with the switching MOSFET capacitance and shows up as a ringing on the switch node shown in the voltage versus time oscilloscope measurement on the right. Now that we have a good understanding of the PI ecosystem and the three sources of power delivery, it is time to look at the details of capacitor placement using an FPGA case study. Here is a case study using a realistic 16-layer PCB stack-up with an FPGA load. This design is leveraged from the ZCU 104 characterization board that was used in the DesignCon 2021 capacitor placement paper. To focus on the capacitor placement and simplify the problem for analysis, a 5 by 5 inch square printed power delivery network was chosen for the VCC power rail surrounding the FPGA load, or sink as it is often called in simulation. The power rail is on the middle layer 10 of the stack-up, and the VRM power connection is located on one edge of the PCB. 3 case studies are used for the capacitor placement simulations. The first, shown in the bottom left, is to cascade all of the capacitors on one side of the FPGA to deliver the power to the load. The second is to evenly distribute the capacitors around the FPGA sink. The third case is the same as the second, but that the medium-sized capacitors are pulled back from the edge of the FPGA to provide more routing space for I/O signals and potentially reduce crosstalk caused by limited routing space. These simulation test structures keep the same physical size while varying the capacitor placement and PCB stackup. Comparing case 1 with the cascaded capacitors with the surrounding capacitors of case 2 shows that for the exact same number and value of capacitors, there is an improvement when surrounding the load symmetrically with the decoupling capacitors. The graph on the left shows the reduction in impedance for the blue trace of case 2 with the surrounding capacitors. And the plot on the right shows that even the noise transfer from the VRM to the sink is improved. The noise transfer is determined by the voltage at the FPGA sink divided by the input noise voltage at the VRM, plotted in dB versus frequency. This experiment was done with both cases using a 20 mil separation between the power and ground layers. It is this PCB-EM model, not a simple lumped SPICE simulation, that shows the lower inductance, lower Q resonances, and less noise transfer when surrounding the load with the decoupling capacitors. Next, the better performing case 2 with surrounding capacitors is used as the starting point to see if the impedance can be further improved by reducing the dielectric thickness between the power and ground layers from 20 mils to 3 mils. This simple fabrication change to the stack-up shows an improvement with the thinner 3 mil dielectric shown by the green trace when compared to the original 20 mil dielectric shown in red. The thinner dielectric reduces the inductance by shortening via connections and parallel plate path inductance on the plane layers. The thinner dielectric layer also reduces the noise transfer from the VRM to the sink at higher megahertz frequencies. In this experiment, the loop area between power and ground vias is reduced with the thinner dielectric layer. This reduces the inductance of the PCB PDN, which results in fewer capacitors required to reach a desired target impedance at the higher frequencies. One of the biggest challenges with the larger high-density BGA packages is fighting for routing space to get all of those signals in and out of the package on a multi-layer printed circuit board. Capacitors placed directly under the FPGA sink can have some of the lowest parasitic path inductance to the FPGA. But what about the capacitors surrounding the load? How close do they need to be? In this Case 3 experiment, the Case 2 design with the surrounding capacitors is modified to pull back the medium-sized capacitors further from the FPGA to allow for more routing space. The very small decoupling capacitors directly under the FPGA are the same in both Case 2 and Case 3, and both cases are using the better 3 mil thinner dielectric. The result, shown in the graphs, shows very little difference between the two cases, just a slight shift at one of the minor resonant peaks. Here we see that the capacitors under the FPGA provide the lowest high-frequency impedance. The next larger capacitors can be pulled back from the FPGA with minimal impact to free up routing space and avoid crosstalk with the other signal nets. Using what we have learned about decoupling capacitors, let's try it out on the real-world test case of the ZCU104 Xilinx evaluation kit using a 3-step power integrity workflow. This example is available on YouTube entitled Pathwave ADS Power Integrity Simulation Workflow with PI Pro, and it includes a download link for the Keysight ADS PI Demo ZCU104 workspace. This DC-AC time domain workflow highlights the importance of using EM simulation to get the PCB parasitics correct and using measured models to ensure accurate ESR and ESL parasitics for the capacitors and VRM inductance. The first step in the PI workflow is the EM simulation of the DC IR drop to ensure that the setup is valid and that the expected voltages are delivered to the load without excessive current densities. Step 2 is the AC analysis to create the impedance versus frequency model for the PCB PDN with decoupling capacitors. This model is then exported to a schematic for the Step 3 transient simulation to look at the voltage ripple on the power delivery network. Pathwave ADS makes it simple to do this whole three-step workflow from within one tool. The AC simulation step makes it possible to design the capacitors for flat impedance and explore capacitor placement options by turning capacitors on and off with different values using the optimizer. The time domain step lets one look at the power rail ripple for final performance verification. Let me take a moment to show you this ADS workspace. It has a hierarchical README schematic that lets you easily push into the sub-schematics like this layout here of the imported PCB CAD data. And then from this layout window, I can open my EM tool, PI Pro, and I have a saved setup, the VCC and power rail analysis. And here now you can see the 3D EM model of the printed circuit board that has been brought in. Initially, you can see I don't have the layers turned on, but I can expand things and turn on all of those layers of the printed circuit board. It just makes it very difficult to see the power rail of interest that I want to look at. So here you can see all those layers turned on, but what I really want to do is turn off those layers and highlight just the VCC power rail that I want to analyze. I can also take a closer look by turning off the components and just looking at that VCC and power rail copper connections there and vias. Next, I can highlight the VRM connection on the right and the sync or FPGA connection on the top of the board there with all the BGA connections. Now, this is my 3DM model of that VCC and power rail. It goes down through the board to layer 10 and back up to the FPGA. I can also, with my DC analysis, quickly look at the current densities just to make sure that things are flowing the way I expect in order of getting the power from the VRM to the sink. And you can see here the connections there. I can also analyze in the frequency domain. I can run my AC analysis now on this setup that I have, and I can include all of the capacitors. And I can look at the power delivery at low frequency here and what happens when I go up to high frequency and capacitors from around the FPGA deliver power versus at low frequency where all the power comes from the VRM and the larger capacitors. Next, I can take and look at, say, optimizing for flat impedance. You can see here in green, I've looked at a location at the FPGA on the back of the board underneath the FPGA, as well as the blue trace, which includes the package die model. Now I can take this optimization design that I have and generate a test bench for use in the ADS schematic for transient and S parameter simulations, and get obviously the results here on a data display. Now I can go back up to my README schematic where this three-step workflow is, but included in this workspace with this YouTube video is also a more detailed README schematic that includes some of the exploration I did taking the original simulations and then optimizing the decoupling capacitor and creating a new analysis to look at. You can see that was as easy as just replacing this PCB PDN EM model for the different optimizations that I did and rerunning the transient S parameter data. So now let's go back to my slide presentation. This ZCU104 example can be designed for flat impedance PDN decoupling, and in doing this, one finds some interesting results that a simple lumped SPICE simulation would not show. Under the FPGA is a group A of small 470 nanofarad capacitors, shown here in the bottom left. Because there was limited space, additional group B 470 nanofarad capacitors were added off to the side of the FPGA, close to some of the other medium-sized capacitors. The graph on the left shows the impedance measured at the VRM in green and the impedance measured at the FPGA pins in blue when only the group A capacitors are on and the group B capacitors have been removed. The graph on the right shows what happens when the group B capacitors are added back in. The PDN inductance at the FPGA pins increases from 32 picohenries to 44 picohenries. The main point is less the magnitude of this change and more that the impedance got worse when adding more capacitors due to the complex interactions between the capacitors. This shows how simulation with EM models can be used to remove capacitors without degrading performance. This optimization in the impedance domain for flat impedance design can then be checked in the time domain to compare the time domain power rail ripple with the original design. Here we see the VCC power delivery network schematic in the top left with the VRM, PCB, PDN, EM model, package die, and dynamic load running at 30 MHz. This simulation uses both S-parameter and transient sweeps to get both impedance and transient data. The results in the bottom right show that the VCC power rail ripple at the die has decreased from the original dash trace to the solid trace. However, since the optimization was done for flat impedance at the die, the ripple at the VRM was allowed to increase since it did not impact the performance at the die. This ZCU 104 evaluation kit example is an already optimized design, so we don't see a significant benefit to further optimization, but it does let us explore trends as we have shown here today. In summary, the three sources of power delivery are the VRM supply, the printed circuit board PDN decoupling capacitors, and the package die capacitance. Designing flat, matched impedance across these three sources of power in the frequency domain provides a resonant-free optimum power delivery. Power delivery is the optimization of a multidimensional power integrity ecosystem. When designing, be sure to use PCB-EM models to get it right. Simple, lumped SPICE simulations fail to get the PCB parasitics correct. Be sure to use the right capacitor model without mounting inductance when connecting to an EM model in simulation. Be sure to select a VRM with lower inductance to reduce the bulk decoupling capacitance required. Be sure to select devices that maximize the capacitance in the package so that it is easier to design the PCB PDN with fewer capacitors. When placing capacitors, remember that capacitors can resonate with other capacitors, forming a noise-generating pi resonator. Finally, I encourage everyone, after watching this webcast, to explore the Xilinx ZCU 104 case study example that I used for this capacitor placement case study and discover how placement does matter, but requires optimization of the whole PI ecosystem to get the answer right. So not just capacitor placement. Here are some of the additional resources. First is the DesignCon 2021 capacitor placement paper that this webcast is based on. Second is the link to Steve Sandler's Keysight-sponsored How to Design for Power Integrity 5-part video series for a deep dive into power integrity basics. The third item is the most recent YouTube video that I did on the power integrity simulation workflow with PI Pro. And this video has a downloadable ZCU 104 ADS workspace that I have been showing in this presentation. At the bottom are the links to the webcast series that include this presentation today if you would like to share them with your colleagues. I hope you enjoyed my presentation, and now let's go back to our moderator to see what questions we have.